The sun begins to dip below the horizon, casting a golden hue across the restless waters of the Gulf of Mexico. On the surface, nearly half a mile above the seabed, the colossal structure of a semi-submersible drilling rig floats effortlessly. Measuring over 100 feet in height and displacing upwards of 20,000 tons, this engineering marvel holds its ground amid towering waves and gusting winds, a delicate dance of buoyancy and stability. Millions of dollars nestled within, this floating giant operates in the depths of the ocean, tapping into resources hidden beneath layers of rock and sediment. As waves roll and swell, the rig's pontoons remain submerged yet resolute, a testament to the calculated engineering behind this leviathan. But the question looms, why do deepwater drilling rigs float on pontoons instead of simply resting on the seabed? At first glance, one might assume that a structure so massive, built to operate in the depths of the ocean, would anchor itself firmly to the seabed. After all, many machines on land rely on solid foundations. However, the challenges of oceanic engineering require a different approach. A drilling rig, in essence, is wrestling with the fierce forces of nature, the heaving waves, ferocious storms, and deep ocean currents. The crux of our mystery lies in understanding how engineers mitigate these challenges, achieving both stability and mobility. By the end of our exploration, you will grasp the remarkable reasons behind this floating triad of engineering ingenuity. To comprehend why semi-submersible drilling rigs employ submerged pontoons, we must delve into the physics of buoyancy and stability. Traditional ship designs rely on a single hull, which bears the full weight of the vessel. Semi-submersible rigs, such as the Deepwater Horizon class, on the other hand, utilize a unique configuration of submerged pontoons. These pontoons extend horizontally, creating a large waterplane area beneath the surface. This design allows them to float not just on the surface but to partly submerge in the water, effectively lowering the center of gravity and significantly enhancing stability. Consider a simple analogy. Imagine dragging a heavy heel downhill. If the heel remains vertical, it topples easily. However, if you lower that heel to a flat position, the weight distributes evenly, stabilizing your stance. Semi-submersible rigs follow this principle. When submerged, the pontoons create a larger area of contact with the water below, counteracting the forces of waves and currents that would otherwise induce substantial motion. Engineers estimate that with their submerged design, these rigs can reduce wave-induced heave motion by up to 90% compared to traditional hull-form vessels with the same displacement. Take, for example, the Deepwater Horizon's predecessor, the Ocean Ranger, which was a semi-submersible rig that operated in the late 1970s. The Ocean Ranger could drill in depths of up to 8,000 feet and had a standard displacement of nearly 21,000 tons. Its design featured large cylindrical pontoons that remained submerged while leaving sufficient hull above the waterline. Despite operating under severe environmental conditions, the Ocean Ranger's stability was significant, enabling it to maintain accuracy in drilling operations, a feat simply unattainable with conventional anchored rigs. The apparent common-sense intuition might be that anchoring a heavy rig to the seabed is the best way to ensure stability. However, that approach poses multifaceted challenges. Anchors are not foolproof. The ocean floor can be unpredictable, with soft soils or rock formations that may not securely hold an anchor during tumultuous weather. This is where semi-submersible rigs shine. In 12-foot swells, these rigs can continue to operate with remarkable precision because they ride the waves rather than resist them. The submerged pontoons act almost like stabilizers in a boat, allowing these massive structures to adapt to the changing sea conditions without compromising safety or operability. As we ponder the effectiveness of this design, consider another engineering approach, tension leg platforms, or TLPs. These structures also utilize buoyancy but differ significantly from semi-submersibles. TLPs, anchored by tendons to the seabed, offer enhanced stability against lateral forces, but the trade-off is a reduced operational envelope in rough weather. In contrast, semi-submersibles excel across a broader range of conditions, offering flexibility in both depth and wave height. The floating nature of semi-submersibles enables a continuous drilling operation, creating a formidable advantage for the oil and gas industry. At this point, one might ask, which of these machines would you least want to be standing next to? This question intimate recognition of the inherent risks involved in drilling operations in the unfathomable depths of the ocean. Each design choice impacts safety and operational effectiveness. Let's now examine the twist of assumptions regarding stability and the benefits of buoyancy. A common belief is that a heavier machine inherently feels more stable and secure when placed on a firm base. The truth is more nuanced. Engineers consciously design semi-submersible rigs to float rather than anchor. In a drastic weather scenario, such as a hurricane, an anchored rig could risk capsizing as it becomes a stationary target while powerful waves crash against it. Conversely, semi-submersibles can weather these conditions by rising and falling with the wave motion, allowing for a better distribution of forces. Surpassing conventional models, these rigs adapt to their environment rather than resist it, a revelation that challenges preconceived notions about weight and stability. The engineering achievement of semi-submersible rigs is integrated intricately with advanced stabilization systems. These rigs employ a sophisticated arrangement of active and passive stabilization mechanisms that continuously monitor sea conditions, adjusting their buoyancy and stability in real time. For instance, the Deepwater Horizon utilized a system of ballast control that allowed the rig to adapt its weight distribution, achieving an optimal balance that aided in efficient drilling operations. By distributing water ballast among its submerged pontoons, the rig could raise or lower its center of gravity based on the conditions encountered. The evolution of deepwater drilling technology relies heavily on innovation. In the years since the Ocean Ranger, the industry has shifted dramatically towards leveraging the principles of semi-submersible design. Companies investing in these rigs understand the implications of stability in drilling efficiency. As a case in point, the West Java, a semi-submersible rig launched in the early 2000s, operates in water depths of around 14,000 feet, with the capacity to drill wells up to 10,000 feet deep beneath the seabed. The engineering advancements seen in its design have optimized both buoyancy and stability further, enabling operations under conditions once thought impossible. In summation, the trick behind why deepwater drilling rigs float on pontoons instead of resting inconspicuously upon the seabed lies in harnessing the power of buoyancy to balance stability and adaptability against the sea's unpredictable moods. The submerged pontoons mitigate the incessant assault of waves and currents, allowing these engineering titans to operate efficiently and safely where few machines dare to tread. As we conclude this exploration of semi-submersible rigs, reflect on the ingenuity present in such designs. These structures embody an audacious pursuit of understanding and adapting to nature's elements. They stand as a testament to human ingenuity, balancing on the delicate line between innovation and engineering integrity. We are surrounded by impossible machines that somehow just work. Subscribe, one giant decoded at a time. The beauty of the semi-submersible design goes beyond mere buoyancy, it's also about how these structures manage and distribute the immense forces they encounter while at sea. Each pontoon is carefully engineered to withstand changing pressures as waves rise and fall, contributing to a mechanical ballet in which far more than just buoyancy is at play. For instance, let's consider the role of these pontoons under specific environmental conditions. On a rough sea day, when waves reach heights of up to 30 feet, the stability of the rig is put to the test. Each pontoon behaves like a floating elephant, resilient and powerful beneath the waves. Engineers expertly calculate the buoyancy of each pontoon to ensure that, even in the worst weather, the rig will not be upended. The cross-sectional area of these submerged pontoons can be roughly 50,000 square feet. This large surface area is crucial because it resists sideways forces, allowing the rig to ride out high waves while providing stability unmatched by traditional anchored structures. Moreover, the integrated design of semi-submersibles ensures that they can not only withstand the forces imparted by waves but also those from drilling operations. When drilling deep into the seabed, tremendous forces are exerted. For example, when a drill bit penetrates rock layers thousands of feet below, the combined weight of the drill string, sometimes reaching over 1,000 tons, applies considerable downward force. The semi-submersible design allows the rig to maintain its position despite these forces. The increased stability of the pontoons aids in the accuracy of drilling operations, which is fundamentally crucial when accessing oil and gas deposits buried deep under layers of rock. One illustrative example is the West Aurora, a state-of-the-art semi-submersible drilling rig designed for extreme conditions in the North Sea. This design features a water tightness and structural integrity tested via extensive engineering simulations and ocean trials. The West Aurora can operate at water depths exceeding 10,000 feet, with a drilling capability reaching nearly 7,000 feet beneath the seabed. Its success in such an unforgiving environment stems, in part, from its buoyant design, allowing it to operate effectively and safely in turbulent waters without submerging too deeply. To appreciate the remarkable construction of these rigs, one must also recognize the sophisticated mooring arrangements they employ. Semi-submersibles are often linked to the seabed through cables or chains, which, contrary to what one might assume, do not act as anchors in traditional sense. Instead, these mooring systems allow for a certain amount of free movement while ensuring the rig does not drift away entirely. Just as a tree bends but does not break, these rigs can withstand significant forces while remaining anchored but capable of moving in response to the waves. One notable case where this capability was critical was during a fierce storm in the Gulf of Mexico, when the semi-submersible rig Papillot observed winds exceeding 75 miles per hour. While conventional platforms struggled or even capsized, the Papillot was able to adapt and maintain operational status. Engineers estimate that the mooring system provided more than 500 tons of resisting force against the storm's winds, allowing the rig to simply float over the raging ocean while gathering valuable data and creating a safer environment for the crew. Furthermore, as we explore the intricacies of semi-submersible technology, it is important to spotlight the advancements made in real-time monitoring and control systems. These sophisticated systems draw upon a wealth of data collected not only from the rig itself but also from surrounding maritime environments. They analyze wave patterns and weather forecasts to preemptively adjust ballast and buoyancy levels. By deploying sophisticated algorithms, an array of sensors can adjust water intake and weight distribution across the craft, ensuring constant stability. This adaptability underscores the evolution of semi-submersible technology. Long gone are the days of simply floating with the waves, replaced by an advanced system that actively combats the turmoil beneath. With the entire rig optimized for operations, the implications for human safety and environmental stewardship become clear. The modern semi-submersible rig, like the Deepwater Invictus, features a layout designed not only for human comfort but also for maximum safety. Each living quarter is strategically located above the waterline, with escape strategies in place. In case of emergencies, the crew can retreat to elevated areas equipped with fast escape vehicles and emergency plans that minimize risks during drilling operations. This adds another layer to the engineering behind semi-submersible design, managing the practical and human aspects alongside the mechanical truths of nature. Such advancements in deepwater drilling technology bolster the industry's commitment to sustainable practices, where innovative designs lift the environmental burden lifted by drilling operations. Intricate measures now in place to prevent leaks and spills are complemented by semi-submersible rigs' mobility. For example, the Oscar B semi-submersible used cutting-edge environmental monitoring systems during drilling operations, leading the charge in ensuring that any disturbances are minimized and detectable in real time, ensuring that human intervention causes no lasting impact on vulnerable marine ecosystems. Let us also not overlook the passionate pursuits of individuals driving these innovations. Engineers and designers work tirelessly to push the envelope of what is possible with semi-submersible rigs. Their work is often a blend of art and science. They extrapolate from traditional shipbuilding principles while integrating contemporary technologies that redefine stability, capability, and safety. As we ponder the future of semi-submersible design, it becomes clear that adaptability remains key. Engineering firms now deploy sophisticated virtual reality simulations to test new designs before they enter production, transforming the conceptual designs into realities that push boundaries and reshape expectations. From various hull shapes to pontoons of differing dimensions, each iteration explored ensures that the industry evolves in concert with the challenges posed by nature, providing both safety and efficiency in operations. In conclusion, as we encapsulate the experiential journey through the fascinating world of semi-submersible drilling rigs, it becomes evident that the balance of engineering and nature offers a suite of solutions that address not only the complexities of oil extraction but also the unyielding forces of the ocean. Floating on submerged pontoons, these engineering giants reveal that sometimes, the most resilient solutions come not from being anchored down but from learning to float gracefully amid turbulence. We are surrounded by